All right, class, this is 20.4 notes on electromotive force, EMF. Water only spontaneously flows one way in a waterfall. That's true also when we're talking about electrons in a voltaic cell situation. So we have our anode, which is the negative part, the cathode, which is the positive part, and the difference between the two of them would be then the potential to move electrons from one side to the other. Such as like how high is the waterfall. If it's a really high waterfall, then there's a great potential. Like in other words, a huge difference between the top of the waterfall and the bottom of the waterfall. That's when we have like a strong battery. Now, the water then would be, of course, the electrons, analogous to the electrons. So what if you have a stream that has a waterfall? Then there's not nearly as much water that goes over. Even if it's a really high waterfall, there's still not that much water. So the number of electrons that are moving from one place to the other is different than the potential, in other words, the pushing of the electrons from one side to the other. So we'll get into like the electrons later on, but the important part is the difference, and that's what we're going to talk about. When I say difference, I mean the potential. So like a voltaic cell can have a high potential or a low potential, obviously, or somewhere in between. But that's not discussing how many electrons are moving, it's just discussing of what the difference is between the anode and the cathode and how quickly the electrons get pushed from one to the other. So let's talk about this. So electrons spontaneously flow in one direction in a redox reaction, from higher potential to lower potential. That makes sense to us. So to make it work, though, we've got to like name it. We've got to come up with a standard then. And let me show you, I'll show you what the standard is. So it says the potential difference between the anode and cathode cell is called the electromotive force. It is also called the cell potential. And that is like the energy of the cell, which is, we're going to be using this quite a bit. So cell potential for 1 volt is 1 joule over coulomb. And we'll talk about what joules and coulombs. So you already know what joules are, but coulombs, that's new for us. So here's the deal. We have everything that you see in this chart here is based on the acidic hydrogen with a +1 charge gaining 2 electrons in a reduction and changing to H2. That is 0, and everything else is compared to that. So some things have a positive potential in comparison, and some things have a negative potential in comparison. I think of it like how we based density. Everything with density is based on the 1.00 grams per milliliter excuse me, of water. Some things are higher in density than water, and some things are lower in density than water. So here it explains just that. Notice that's aqueous. Notice that's 1 molar, which is 1 mole per liter. And that, that's a gas, and that our pressure is in 1 atmosphere. Okay, so this is just the conditions of defining what the potential is between two sides of this reduction. Okay, so let's move on. So standard cell potentials. Now here's really the meat. Here's really what the working equation we're going to be using for the problem sets for 32, 38, whatever they are, the problems for 20B. So E cell in this standard just means what it did before. It means at 25 degrees under normal circumstances. Notice that these both say E and then reduction. The reduction here is in reference to how each of these types of reductions, they're all reduction half reactions. So you may see something that's a negative here, and that means that it probably exists more commonly as an oxidation, which means that it would prefer to go, like for this one here, for nickel as a solid, would prefer to go in this direction, to change into nickel as a +2 and give off 2 electrons, instead of being nickel +2 and go into nickel as a solid. So when we change that, then we can change, like if I write this as an oxidation, which I just did, then I can change the sign for the volts that I have there. That's not very clear, but you get the idea. So instead of a negative 0.28, once I write it as an oxidation, then I can change the sign to make it a positive 0.28. Okay, so you're going to notice that we have the cathode, which is the reduction part, and we know that oxidation happens at the anode. So I take my reduction, I subtract it from my oxidation, and I can write both, since both of them are written as reductions, I'm taking the reduction minus the oxidation, but you can keep them as reductions, so you don't have to change the sign of anything, because the minus does that for you. I'll show you as an example problem. So cell potentials for oxidation of the cell. Notice that we have the reduction is listed as, this is the oxidation part, but they're all listed as reductions, a negative 0.76 volts. And for the reduction, this side over here, the cathode, here, we got a plus 34 volts. So that means that when we take the numbers and we do our cathode minus anode, we end up with a positive 1.1 volts. So, oxidation and reducing agents. So the strongest oxidizers have a positive reduction potentials. Okay, let me say that one more time because this is important. The strongest oxidizers have the most positive reduction potentials, and since everything's listed as a reduction potential, that means when we go back to this chart there, that the strongest oxidizers are here at the top, and the strongest reducers are at the bottom with the negative. Okay, let me get back to this now. So the strongest reducers have the most negative reduction potentials. Okay, that's good to know. So strongest reducing agent is down here. For lithium, the strongest oxidizing agent is fluorine up here. Excellent. Oxidizing and reducing agents. So this is the one we just had with zinc going to a +2 and electrons. This is the oxidation. There's the reduction potential written as a reduction, of course. And here is the reduction at the cathode. The cell potential is the difference between the two of them. Notice that hydrogens, I should say, it should be written as, that's a 2 in front, +2 electrons going to here like this. Notice that this is 0 somewhere in the middle here. So the potential is from the greater potential to the, well, I should say, the anode to the cathode. And because it goes up, we're increasing in energy. That's how we get the positive 1.1 volts, because it starts off low and goes positive. Just another way to explain that. This is 20.5, but I'm going to take a second here to just talk about this. Notice that we got delta G from last chapter. So our redox equation can be found by the minus the N. This is the Faraday's constant here. This is our energy. And this, of course, is the same N. That means numbers of moles. Okay? So the Faraday constant is this one here. That's coulombs per mole. Then we can use the E, obviously, is the one that we've used before for energy. Now we can also use, let me just get moving here to something that we can use. So remember the delta G, that means blah, 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 blah. So let me just keep going here so we can get to what we got. So first thing we do is we find the E standard using the potentials, the reduction potentials on the chart. That would be E cathode minus E anode, okay, or oxidation minus reduction. So reduction minus oxidation. Sorry, I said that backwards. So that's how we get this E standard here, and then minus, and then we can use this number, because we'll use, this is crap here. This should be log Q, like that. Okay, Q, do you remember what Q is? Q is equal to K. K is products over reactants for such as, quick example, if these are all gases, then you could do K is equal to H2O. I know you remember how to do all this. It hasn't been that long. And we have, so this would be K. Now if it's not at equilibrium, then this wouldn't be K, this would be Q. We don't know what it's at. And then we would use this to figure it out. So this is the same equation that we would use here for Q. So if we're looking for a non-standard energy of a redox reaction, I would use this. We know that this is Faraday's constant. This is the number of moles, whatever we're looking at. This is the standard R, 8.314, I believe. I'll check that to make sure, though. And then, of course, our temperature is going to be in Kelvin. Okay, so we will do some problems with this. I just want to make sure that you guys got a chance to see that. We can also use the Nernst equation as this once we put all of these together, because the temperature for standard is 298. Then we can just use this number here. We can still use the natural log. That should be log of Q. I don't know why they keep screwing that up. So there's an easy way to get this all to work out. So there's the Nernst equation. We'll use that pretty often. Last bit on the Nernst equation implies that a cell could be created that has the same substance in both electrodes. For such a cell, E cell would be 0, but the Q would not, which means that the concentrations are different, then the E would not be 0 either, because if we go back to here, if this is 0, that doesn't necessarily mean that this term or this term is going to be 0, right? So this will be something other than 0, which means my E here will be something other than 0. So that still works. So you can still have two different things. You can have two the same things but in different concentrations and have it still all work out. Okay, that's all I'm going to talk about. This was long enough. I'll elaborate in class and with problems.